Okay, let's go for the next topic. The next topic is gonna be dielectrics. Dielectrics are just insulators, like wood, plastic, paper, correct? And when these insulators are placed inside of a capacitor, the name is dielectric. Okay, let's try to see what happens to the capacitance, right, when we use a dielectric. Remember, capacitance is defined as the charge divided by the voltage, and for two plate parallel plate capacitors, we have that the capacitance in vacuum or in air, right, very close to vacuum, it's gonna be epsilon naught area times the distance between the two plates. Okay, imagine that we have a battery that charges the two plates. So we have initial charge on the plates. What happens if we introduce an insulator? Well, it's found, this is by experiment, that the charge increases by one factor. Now, imagine that we increase the voltage, let's say 12 volts. At the beginning, we have more charge without the insulator, but when we place the insulator, right, the charge increases. But the factor is the same, right? The factor is the same using 6 volts or using 12 volts. Means what? Means that in this case the charge is equal to a factor times the initial charge, right? And this letter is called kappa. It's a Greek letter, kappa, and this is called the electric constant, dielectric constant. And that depends on the material. Could be plastic, could be paper, could be glass. It's different. Great. Now let's see what happens to the capacitance. At the beginning, remember right here we have this capacitor has this capacitance, and this capacitor the final capacitance. Okay, using these concepts, what do we have? Capacitance is defined according to this equation, right? Q naught divided by voltage. Voltage is gonna be the same for both cases, right? And the final capacitance is gonna be the final charge divided by the voltage. From here, look, from here, if we divide charge over initial charge is equals to kappa, correct? Let's see what happens in this case. What happens? Well, let's divide these two quantities. And what do we have? Capacitance using vacuum, capacitance using the dielectric is equals to charge, right? The beginning divided by final charge. Correct. Now let's try to use this quantity right here. So this is equals to, you can see it's gonna be the inverse of kappa. Or kappa inverse, correct? Now from here we can conclude that the capacitance, final capacitance, is equals to kappa times the initial capacitance, right? So the capacitance at the end increases too. If we increase the charge, right, we increase the capacitance, correct? So capacitance is equals to kappa times the initial capacitance, correct? Perfect. Now, what happens when we involve this quantity? We're using this one first. Now let's see the definition for the capacitance when we have a parallel plate capacitor. Let's do it. So what do we have in this case? Well, the same concept, right? At the beginning we have epsilon naught area divided by the distance, correct? And right here we have the final capacitance equals to epsilon naught. But before that, look, this is gonna be the final capacitance equals to epsilon naught times this. But let's apply this equation right here, correct? We know that final capacitance is equals to kappa times the initial capacitance, correct? Kappa initial capacitance is gonna be this quantity. Perfect. It's gonna be kappa, right, epsilon naught times area divided by d. Right, so we have then that using these quantities, the final capacitance equals to kappa epsilon naught area divided by the distance right between the two plates. Great. Now let's go for the other case, and for the next case it's gonna be removing the battery and see what happens. Okay, let's do it. Remember, in this case, we are dealing with the charge. Now let's do the next case dealing with the voltage. Great. Now for the next case, we have again a capacitor, right? A capacitor like this, and we charge it using a battery. So this is positive, this is negative charge. Okay, and in the beginning we have this initial charge, which is the same in magnitude, opposite in sign. Now let's remove the battery. Imagine this voltage is 6 volts. Let's remove the battery, right? And let's look for the voltage. And it's found that the voltage stays the same, right? Voltage is the same as when we have the battery connected to these two plates. Now let's introduce an insulator, right? That we call it dielectric. Perfect, let's do it. So the same thing, right? This is the charge is the same as at the beginning, correct? But what happens when we put an insulator, correct, inside? Okay, let's do it. When we put an insulator inside, it's found that the voltage decreases, right? So this voltage is gonna be less than the initial voltage. Right, let's call this initial voltage right here. This is, let's say, final voltage. So the final voltage is less than the initial voltage, correct? Now, imagine one more time, this is 6, well, we have this condition. Now let's increase this to 12 volts, and repeat the experiment. It's gonna be 12 volts, right here it's gonna be 12, and also right here the voltage is gonna be less than right here. But the factor is the same in these two cases. It is similarly to the case when we have charges, correct? So in this case we have that the final voltage is equals to the initial voltage divided by a factor kappa. Right? It's the same factor. Correct? So this is found in the experiment. Voltage is equals to the final voltage, right, when we have insulator, is the initial voltage divided by the property of the insulator. This is represented by kappa. This is dielectric constant. Correct? Now let's see what happens. By the way, kappa, as you can see from here, must be greater than 1. Now let's involve the electric field, for instance. Remember, voltage is defined as the electric field times the distance. Imagine that that's the final voltage, or the voltage using dielectric. What happened at the beginning in vacuum? Well, this is in vacuum. We have the same electric field divided by this is the electric field. This is the electric field of the dielectric, correct? Now this is the electric field when we have vacuum. Perfect. Now let's divide this two because we're looking for this condition one more time. We have this difference in voltage divided by this is equals to the inverse, right, of kappa. Okay, let's apply this condition right here, correct? And what do we have? Let's divide these two quantities, and we have that is equals to the electric field over the electric field in vacuum, correct? Now, but what is this? This ratio is coming right from here, and this is equals to, as you can see when we compare these two, again right here is gonna be 1 over kappa, right? 1 over kappa is equals to this and is equals to that. Now let's see what happens to the electric field, right? So the electric field of the dielectric divided by the electric field in vacuum is equals to the inverse of kappa. Correct? Now, what happens then to the electric field? So the electric field, is this one correct? Is this one correct? Okay, let me see if this one is correct. Okay, and then we have that the electric field, right, at the end is equals to the electric field in vacuum divided by kappa. Correct? Perfect. So we have then these relationships. One more time, the electric field using dielectric is equals to the electric field in vacuum divided by kappa. This is coming from this analysis right here, correct? Right here. Perfect. Now, well, we found also, okay, we have that the voltage, right, using dielectric is equals to voltage without the dielectric divided by kappa. Correct? Perfect. Now, let's see what happens when we introduce this concept to the energy density. Okay, let's go to the energy density. Energy density is defined, remember, energy density is equals to 1/2 epsilon naught, correct, E naught square. Now, when we introduced the dielectric constant, we found that this energy density is equals to 1/2 kappa epsilon naught times the electric field. Correct? This is when we have the dielectric. This is not dielectric with dielectric. Correct? Using dielectric, then energy density is equals to 1/2 kappa epsilon naught times the electric field in the dielectric. Right? Perfect. And the same thing we can use, for example, for Gauss's law. It says the integral, correct, of the electric field and the area is equals to the charge divided by epsilon naught. Right, but this is the case when we have epsilon naught gonna be E naught. Now, what happens when we introduce this quantity? Now, using dielectric, this becomes, in this way, it's gonna be kappa, right? That product of the electric field in the dielectric times the area is equals to the charge epsilon naught. Correct, and this is the case when we use the Gauss's law. Let me write it right here. It's equal kappa, correct, times the electric field, the dot product of the electric field, the area equals to the charge divided by epsilon naught. Correct. Great. Now let's see what happens for, with the dielectric, right, inside of a capacitor. Let's do it this way. Imagine that we have this capacitor, correct? Imagine. Okay, and of course we charge it. It's charged. Of course, we have right an electric field. Right, the electric field without a dielectric. What happens when we place a dielectric in between? Well, now let's do it. Imagine this is the dielectric right here, correct? So this is positive, right? And this is negative charged. So one more time, this is the charge, right? At the beginning, the charge. At the beginning, this is the charge, right? At the end, and the charge right at the end. Right, because we don't have a battery, right? The charge stays the same. Perfect. Of course, the voltage decreases. We found it. We found it before. Great. Now, what is happening then? Well, look, this positive charge attracts negative charges right here, and this negative attracts positive charges right there on that side. Correct. Now, right here we have the electric field, right? Without the dielectric, but inside, look, we have an electric field in opposite direction, right? This is the electric field inside, right, of the dielectric, correct? And again, right here we have the electric field without the dielectric. Now let's pay attention on the dielectric. What is happening? The electric field, right, in the dielectric is equals to the difference, right, of these two electric fields, right? The electric fields coming from the two plates, and the electric fields produced by the rearrangement of the molecules, right, inside of the insulator. Look, it seems that they are polarized right inside. Perfect. And then this is equals to, according to this equation, right, we can also represent this in this way for the dielectric, right? For the dielectric, it's gonna be, right, the electric field in vacuum divided by kappa. Correct? Perfect. Now, let's use the Gaussian surface. Correct. One more time. Imagine that this is the plate, the capacitor plate, right? And right here we have the insulator, right? Negative, negative, negative. Now imagine, of course, this was like this. We create a Gaussian surface. Okay. Imagine that this is the Gaussian surface right here, imagine. Okay, so we have inside of this insulator the electric field, right? Inside of the insulator, ED. Correct? Now, let's find the electric field inside of this insulator. Okay, let's do it this way. Let's call this the charge density of, let's say, of the conductor, and right here we have a density, charge density of the dielectric, for example, the dielectric. Okay, this for capacitor, this is for the dielectric. Now let's continue using this formula. So the electric field in the dielectric equals to the electric field without in the capacitor, right, without any insulator. So, and we know that this is found, right, that the electric field is equals to sigma over epsilon naught, but sigma is the charge, right, divided by area epsilon naught. Correct? Now let's do this in this way. It's gonna be the charge, right, for the capacitor, correct, because this is sigma, right? It's a sigma for the capacitor, charge of the capacitor, right? This is for the electric field inside, it's gonna be the dielectric, correct? Perfect. It's gonna be divided by area epsilon naught minus the charge in the dielectric, right? Divided by area epsilon naught is equals to the charge in the capacitor, correct, divided by area epsilon naught. Correct? And then what do we have? Well, this is equals to the electric field of the dielectric times the area is equals to the charge, right? Charge in the capacitor minus the charge in the dielectric divided by epsilon naught is equals to the charge in the in this plate, right, divided by epsilon naught. right? Perfect. And we can conclude the same thing as using this equation right here, correct? So we have that the electric field in the dielectric, we can use the dot product. You want to, in this way, equals to this charge in the plate divided by epsilon naught, which is the same as this formula from the Gauss's law, right? Because this ED, again, the electric field in the dielectric, well, it's just the electric field in the in vacuum of this capacitor divided by kappa, right? Then we create the same equation using this analysis. This is called the Gaussian pure box, right? This is the Gaussian white pure box. This one is the pure box right here. And we got, again, these new formulas for a capacitance when, for the capacitance when we use a dielectric. Okay, well, and with this analysis, we finish this chapter, chapter 24, and I'll see you in the next chapter. Okay, bye.